Welcome to a new test and teardown video. This time it's a Tektronix 2901 time mark generator. I think this design is from about 1970. And this unit here looks like a mint condition. Look how beautiful it is. And we got a few things with these. This model uses silk screened text on top of all the push buttons here. And this wear off quite easily. So I think what we see here is a big reveal. This unit was not used a lot. There is you can probably see this from this lamp here. There is a heated oven for the crystal oscillator, and this is why it's super accurate and stable. It can do all sorts of pulses and repeat times and all that. You can see here from 2 nanoseconds to 5 seconds in a 1-5-10 sort of system all the way. And it's quite modern for 1970. It's full of ICs and transistors. So before I power up good old stuff like this, I really need to open and do a deep inspect. You can run this on an external clock input. And I think they are nice to say it's 50 kilohertz to 10 megahertz the range. I think it will of course affect how everything is if you don't use the exact right clock, obviously. And you can select between internal or external clock. There's another thing you always want to double check, and that is the line voltage switch is correctly set for your country. So now we have to open. Some of the things you really like with Tektronix. Look at that. All you have to do is just carefully flip these. And then like new condition. Wow, what a lucky day. The smell is definitely old. I need to open a window here in a second. This is intense. It smells really old. So if you can hear the birds in the background, it's because now the big door here to the garden is open because I need to breathe. This dust we see here, I just took my finger here. This looks like aluminium dust. I'm not super happy about that. So what is that coming from? Is it from these, or it's not possible, really? So I think I really need to go and give this a lot of compressed air to get all this out. There's probably more. I need to show you this. Look up here, can you see the metal dust? All the way down right here between all the components. So this is something I did not expect to find, and it was also here at the back, exactly the same position. And look at that. We got this hole, and we got this hole here. And it is possible to have metal dust in this tiny little hole all the way around. And that tells me this unit was stored somewhere where they did a lot of CNCing or cutting and filing or something like that, really, really bad. So visual inspections can be very, very good. Let's try and look a little bit at the block diagram first of all, just to get a little bit of an overview of what this unit consists of. So there is a 10 megahertz crystal oscillator that's inside a temperature regulated heater. We call this an oven. And then this 10 megahertz goes into different multipliers. And all those multipliers, they are activated depending on the output frequencies. We got doublers to go to 20, and then we have multiplied by 5, and then we have multiplied by 2, and all that. So we actually got a 500 megahertz multiplied oscillator running that is sort of in lock with the 10 megahertz, but it's of course only activated at the very the fastest output. Then we got all the dividers, and all those divider chips, they are all of them JK flip-flops. So they just divide by 2 and by 2 and by 2, and this is how you get this 1, 5, 10 sort of system. So let's look inside this unit. We can see here is the socket for the oven oscillator, and this will be the oscillator transistor and the inductors and all that. So it's amplifying and filtering the 10 megahertz. And I think the incoming frequency, of course, the external clock should be 10 megahertz as well as this one is, because it goes all the way into all the multipliers and all that. For all that to work, of course, you need to have 10 megahertz. But if you're using all the lower frequencies, then you're using only dividers. And of course, if you're using only dividers, your input external clock can be much lower or higher or anything, or any fraction of whatever. If you're using the multipliers, your incoming frequency must of course be either 10, 20, 40 or 5 or something like that. Then they will more or less lock anyway and get working. So what you see here is the fastest. This one here is a quarter wavelength resonant circuit, and this is the 500 megahertz system. And then you go lower and lower. Here's I think this is 200 megahertz, and then it goes lower and lower and lower. So this switch here is the 500 megahertz output, 2 nanoseconds, and slower. It's quite fun to see how those inductors, they consist of 2 different windings inside each other. This way you can change the resonance and the coupling degree. Here it's also really funny to see how the 2 inductors here, they couple like that, and all the transistors, they are in sockets. So that is nice and service friendly. The circuit board is labeled copyright 1969 by Tektronix, and this unit was released in 1970. So of course they spent a year on the schematics and improvement of the design and all that kind of stuff, but the layout is from 1969. If we look at the bottom side of the unit, got a really nice signature. Oh, let's try and zoom in and see if we can get that signature. Tested by Ray Wood, I guess. And then bottom side here, we can easier see the oscillator. See the oscillator, you can select 115 or 230 volts AC for the heater, And the temperature it regulates to is 75 Celsius. It really heats this up. So this capacitor here is nicely isolated. I also like the fuse is isolated, and then everything here is nice and safe to touch. There'll be some more dividers for all the slow frequencies, for all the trigger outputs and all that. And look at this transistor up here. This one. I'm not super happy about that. I don't think it is causing a problem or anything. It is nicely in the socket. You can actually break the pins or break the socket if you're just trying to fix stuff that is still working and still in good contact and everything like that. So normally I just check there's no short, there's all here is fine, and then I just leave it like this. This will give us a little bit more space if we need to operate the connector here and all that. And this switch here is really hard to operate. This one is handling the marker amplifier, so to give us some more signal. I think maybe it's this one, so you can turn this on and off, but the switch is really bad. It's probably gonna break something. So I want to lubricate that, and I also want to lubricate all the shadow switches, because I can feel when I'm doing something like this, sometimes, see, they are connected mechanically. And when I need to do this, sometimes it's easier this way than this way. But sometimes you need to press really hard for this mechanical thing to work. So yeah, here we go. Yeah, a little bit of lubrication with contact 61, and all this is going to run nice and smooth again. So it is of course working really good. I got all the outputs connected to my scope, and I am using 10 dB through attenuators. And I also use the scope in 50 ohm mode as well. And there's of course a problem with 50 ohms modes. They can't handle a lot of volts. So that is why I needed to have external attenuation, because this output here is 25 volts. So it's a lot of output. And this marker amplifier here is doing positive or negative, and this is a thing with those time mark amplifiers. So positive, let's look at the yellow, is channel 1 here is my output, so you can turn the output off, or you can have it in negative, and this way the pulse goes of course down. So this is my main output pulse, and that will be the marker output in pulse mode. It is this one. And then there is the trigger output. It's the purple curve is the trigger output, and the trigger output you can select different trigger times. So my main output is 50 microseconds, but my trigger output is 0.1 millisecond. That is of course 100 microseconds. You kind of get the idea, right? So here's how it works. 50 microseconds repeat is the same as 20 kilohertz. You will have to work with time and frequency like that, but it's quite easy. Just 1 divided by 1 makes the other one, so it's quite easy to figure that out. And then you can change the different timings. The fun thing is, see the rise time and the fall time. So if I go faster or slower, or even slower, see what happens is the fall time also goes slower and slower. Here we go. Let's see if I can make this. And also even the trigger, see? The trigger also changes its fall time depending on how fast it's repeating. So that is automatically done. So this is 1 microsecond. This is the fastest mode for the trigger amplifier to work, and this is the trigger amplifier output, and that will be the normal marker output, and you see a lot of reflections and all that kind of stuff here. And yeah, my scope is in full bandwidth mode, so this should not be my scope that is to blame for all that. Well, let's try and go a little bit faster and see what happens. So this is 0.5 microseconds, and that seems to be working good. 0.1 microsecond. This is 10 megahertz, of course. Then this happens, and I think it's because if we look at the output, it is now sine wave, because this is 20 megahertz, and 20 megahertz goes via the first doubler. So that is, of course, why it's a sine wave, right? So from now on, we would expect this all to be sine waves. So the next one is the output from the 5 doubler, and this should be 100 megahertz. And here is 100 megahertz. So all that seems to be working. And then the next one should be 200. And I see only this tiny little, and you can see it's looking like this doubler is not working. So the strongest signal here is the 100, and there you have the 200 down there. So it depends if I put my trigger down there, it is counting 200 on my screen, because now it counts all these as well. So I need to fix this doubler, the 200, before I can, well, they're actually, how do you say that? They're isolated. They are not connected. The output of this one is not connected to the other one. So let's look at the 500. See, there's nothing at all. So the 500 is also fed with the 100 megahertz from the previous. This one that we have already proven is working nice and stable. So I got, I got 2 doublers I need to fix. I think it's actually easier to show high frequencies and the components of harmonics and all that kind of stuff on a spectrum analyzer. So this is what I've done, and I've trimmed and trimmed and trimmed for the best possible output. So this is 500 megahertz, and as you see, it is the highest output, and we got 20 dB down to the nearest harmonic. So let's check out. This is 200 megahertz, and we got only 10 megahertz or 10 dB down to the 100 megahertz. And this is the 100 megahertz output. So I think it looks a little bit like we could use a little bit of new transistors in here with a little bit higher gain at the wanted frequencies, maybe a little bit of fine tuning. Yeah, so this peak here is 100. Yeah. So this is how I got this up and running so far. And I think all the different outputs and triggers and modes and all that kind of stuff is definitely working. So I think this is all I wanted to show so far about this time mark generator. So thank you very much for watching. I hope to see you soon again. Bye bye.